So, hello everyone. I'm Ashwini from EPH third year from IIT Roorkee, and in this video, we will be looking for the practical that is studying the characteristic of Lvdt. So, this is the flow in which we will be proceeding. First, we will be looking for the aim, and then we will be looking for the apparatus, then the theory behind it, then the procedure, and then we will be looking for observation and result, and then we will see the precautions that should be taken while doing the experiment. So the aim is to study the performance characteristic of linear variable differential transformer, the displacement versus the output voltage, and we will also be looking for the linearity. So the apparatus can be divided broadly into two categories, the mechanical unit and the main unit. The mechanical unit consists of the Lvdt and arrangement for the fine movement of the core, and the main unit consists of the electronic circuit, the carrier source, signal amplifier, and demodulator. So these things are required to give the input and take out the output from the Lvdt, and the mechanical unit is responsible for the physical movement of the core. So this is the kit for Lvdt, and it consists of the electronics for the Lvdt, and it also has the demodulator, and we have a display for demodulated output. And these are the sockets that are given, so you can actually connect this to the CRO, and then you can just see the wave shape there. And this is the switch for turning on and off. So here this is the CRO, and it is connected to the excitation carrier socket for the of the Lvdt. So this is the input or the excitation that we are giving. So this is the wave shape of that, and this is the mechanical arrangement. So we have a slider, and as we move the slider, then the core changes the position between those two secondary coils. So this is the whole circuit, and the CRO is connected to the modulated output, because from the kit you can only get the demodulated potential. If you want to go for the modulated output, then you need to connect to the CRO, and then you can look it here. So the main construction involves three coils, one primary and the two secondary coils, and an input AC excitation is given to the primary coil. And when the excitation is given to the primary coil, due to the mutual inductance, the voltage or the current is generated in both the secondary coils. And in the balance condition, the core is placed in such a way that the flux throughout both the coils, both the secondary coils, is same. So the potential V1 and V2 that is generated across the two secondary coils, they are equal in the magnitude, and they has a phase shift of they differ in the phase by pi. So they actually cancels each other. So at output we have zero potential. And if there is some electrical or magnetic imbalance, then even when the core is at zero position, we have some residual potential at the output. Now here we can see that as the core moves, so the flux throughout the secondary and then the secondary one and the secondary two, it does not remain the same, because this core is like some soft iron core, and it has a property that magnetic field lines, they prefer to pass throughout the core. So when this core moves this side, it takes the flux that side more. So then H2 has more flux, so the potential will not be zero, the output potential will not be zero, and we will be having some output potential that we can see from here as well. And another thing that we already seen, that they will be differ by pi radian. So they differ by the pi radian. And the output of the Lvdt, that is linear variable differential transformer, it's not linear in every range. It will be linear in some specific range depending upon the construction and the material used. So we'll be taking two readings, one for the demodulated output and one for the modulated output. And for the AC output, you need to connect the mechanical unit to the CRO, and then you can start from one side and just go till another side, or you can start from the zero and then go to either side and take the reading from the CRO, and then we plot the output potential versus the displacement curve. For the demodulated output, we directly take the reading from the display that we have on the kit, and then we plot the output potential versus the displacement curve. So now we will look how we take the reading, how we take the observations for the Lvdt. So you can see that here the scale is at, the pointer is at 0, and we are getting the corresponding potential difference, and we can see the output here as well. And now we vary this pointer by 0.5 centimeters. So we would, and you can see the corresponding readings, and you can see the fluctuations on the CRO as well. And similarly, we again change it. So by varying this length, we record the corresponding potential, and we finally plot a graph that you can see from here. So this is how we take the observations for Lvdt. After taking the observation, we plot the modulated and demodulated characteristics, and we can see from here, this is the demodulated characteristic that I have obtained, and we can see from here that the response is linear in fairly good range, and after particular displacement, it becomes non-linear. Here is the modulated output, and you can see that here when the displacement is 0, the voltage is not 0. So here we have some residual voltage as well. And finally, we calculate the Lvdt constant from the plot. So here the slope of this curve in the linear range gives us the Lvdt constant. Finally, coming to the precautions. So here are some precautions that you should take while doing the Lvdt experiment. So the connections, the wire that should not be loose. And while taking the observation, the core must be moved slowly, and the reading should be taken while they are not fluctuating. And for plotting a good curve, the reading should be taken at a closer interval. So this is how we perform the Lvdt experiment.